All right, welcome everyone to this special current electricity class. So this is a full video tutorial on current electricity explaining every concept in current electricity. This is a topic a lot of students struggle with every year. For those of you who will be taking the Jamb exam, you would know what I'm talking about. So this is a topic that is always seen every year in the Jamb exam. Why? Because it is a very tricky topic. It is very simple when you have gotten it, but if you haven't, trust me, you struggle with it for a very long time. So now, under current electricity, right, you will need to know some concepts. This is what will help you in answering questions on current electricity. That is just it. If you understand these concepts, how they work, what you need to know, what you don't need to do, and all of that, trust me, any question you see on current electricity, you'll be able to dismantle it. So we are going to start gradually because this is a full crash course. What will happen is we are taking it step by step from the beginning stage all the way to the end. We are going to solve a lot of questions. The goal of this course, this video tutorial, is just to ensure that you can solve any question on current electricity by the end of this video. So now, starting with the word current electricity. What does it mean? Now, current electricity involves the flow of electrons or charges around a conductor. This will be displayed in the screen shortly. I wouldn't want to write too much in this so that when we get to the calculative aspect, you understand. But I'll be listening out to main point. Please take note of everything that will be listed that I'll be talking about. We define current electricity as the flow of electrons, right, or charges around a conductor. So basically, current electricity is just, we are just dealing with what? Electrons that are flowing. You understand? So we have defined current electricity, right? Defined. So I'm just going to write this here. Current electricity. Now, moving on, we also have what we refer to as electric currents. Electric current. This is another concept we'll talk about. Electric current. So now, this is the rate of flow of electric charge around a circuit or the quantity of electricity Q flowing per time. Electric current has a formula. I, because this electric current, let's represent it properly. It is represented as I, right? So we can put this in brackets, I. And it is given as Q over T, where Q is the quantity of electricity. Q is the quantity of electricity. Good. And then we have T, which is the time that this quantity of electricity flows, right, per time. So T is our time. So with this, we can easily get the unit of electric current. Quantity of electricity is measured in coulombs, represented by C. Time is measured in what? Seconds. That's the unit. So the unit for electric current, I, is what? Coulomb per second, or we could just say amperes. So this is the most common one I must have been saying. That is amperes. Okay, so moving on, we also have what we call the terminal potential difference, or your voltage, and then our electromotive force, E.M.F. So let me just write this down. So we have the terminal potential difference, or your voltage, the one you know as voltage, right? That's the V. And we also have what we call electromotive force, E.M.F, which is usually represented with the letter E. There's always confusion between this terminal potential difference, right, and our electromotive force. And this is where we are going to clarify it. Now, your terminal potential difference is the work done or energy in volts in moving a unit charge from one point in a circuit to another. In other words, you're talking about the PD or the voltage when a circuit is delivering current. And when does a circuit deliver current? When it is a closed circuit. Please take note. When it is a closed circuit, that is when a circuit is delivering current. Now, for the E.M.F, it is the opposite. It is the voltage or the PD in a circuit that is not delivering current. So it happens in an open circuit. So what we are saying is that in the terminal potential difference or the voltage, energy is transferred from electrical energy to other types of energy. While in your E.M.F, energy is transferred from other types of energy into your electrical energy. For your terminal potential difference, we are dealing with components of a circuit, like your resistors, your light bulb, the LED, the speakers. Each of these components will have what we call potential difference across them. But for E.M.F, we are dealing with power sources, like your cells, your battery, or any other power source. Most of them have what? E.M.F. You get it now? So they are still voltage. So E.M.F, which is presented as E, is given by W over Q. Same with our terminal potential difference. We are still going to talk about more formulas, but before then, note that E is given as this. And since W stands for our work done, Q stands for our quantity of electricity or quantity of charge, right? We said Q here has the unit C, that's coulombs, stands for coulombs. And then work done is in joules. So if we are to put these two units together, we would have something like A over C or joule per coulomb. Okay, so you should also know that there are some factors that can affect the E.M.F of a cell. Remember we said the E.M.F is the voltage when the circuit is not delivering current, when it's an open circuit, right? Now, the nature of chemicals or materials used in that cell can affect the E.M.F of the cell. Take note, when we're talking about the nature of these chemicals, we're talking about the quality of the chemicals. The chemicals here we could be referring to most likely is the electrolyte, because this is what is used to make some of our cells, right? Good. Now, it depends on the quality of these chemicals and not the quantity. The stronger the electrolyte, the lower the internal resistance and the greater the E.M.F. We are getting to the internal resistance. What we mean by this is that if your electrolytes you are making use of, which is serving as our chemicals, where all the materials, well, if it is strong, we can get a higher E.M.F. If it is weak, we get a lower E.M.F. So we don't really need to, even if it's just a small quantity of a strong electrolyte we have, it can produce a higher E.M.F compared to a large quantity of an electrolyte of lower quality. Then another factor it depends on is the number of cells, the time, and the temperature. E.M.F decreases with time and temperature. Take note of that. Why? Because when we're talking about E.M.F, a good example, remember I said this E.M.F, right? We can find E.M.F in power sources such as our battery, cells, and others. A good example of battery is for we have the common batteries we use in flashlights, for example. Those are referred to as primary cells, right? They can run down. This is why E.M.F depends on the time. Can you see it now? So they actually run down in time. So just like me saying, as the time increases, the more time, the more usage, right? You get a lower E.M.F from that cell. You get it. They add the temperature, the what? The lower the E.M.F. So E.M.F decreases with time and also with temperature. Good. We said that the nature of chemicals or materials used is also one of the factors that affect the E.M.F of a cell. Meaning that the stronger the electrolyte, the lower the internal resistance and the greater the E.M.F, right? So we mentioned this particular term, the internal resistance. Now, what exactly is this internal resistance? Let's discuss about it. So the internal resistance is the opposition to the flow of current by the cell producing the current. Note, by the cell producing the current. Now, what this means is that this internal resistance, right, it is actually what determines the maximum current that can be supplied by a cell. Meaning that if a cell have more internal resistance, the lesser current that cell can supply. You get it? So the more the internal resistance, the lesser the current the cell can supply. So we can represent this mathematically by saying I max, let's use I max, equal to E over R, where this I max is given as what? The maximum current. So that is the maximum current. And E still stands for our EMF, while the R is our internal resistance, internal of the cell. So now, just like we have factors that affect the EMF of a cell, we also have factors that affect the internal resistance of a cell. Don't forget, this EMF, if you look at this, this internal resistance of a cell depends on the EMF of the cell. Can you see this? It depends on the EMF of the cell. We said that the lower the internal resistance, the greater the EMF, right? An indirect relationship. Now, what are the other factors affecting this, the internal resistance of a cell? We have the nature of the chemicals or the electrodes, the amount of chemicals or electrodes, and the size of the cell. And then we have the area of the electrodes, and we have the separation or the distance between the electrodes. So can you see now, we have two particular factors that both affect the EMF and the internal resistance, which are the nature of chemicals or the electrodes and the amount of what? Chemicals or electrode. So just like how we have the nature of chemicals affecting the EMF of a cell, we also have the nature of chemical affecting the internal resistance of a cell. And this is true because we said the stronger the electrolytes, the lower the internal resistance and the greater the EMF. Can you see? So there's a relationship between the three of them, meaning that the lower the electrolytes, the higher the internal resistance and the lower the EMF. So now moving on to the amount of chemicals or electrodes and the size of the cell. For the internal resistance, the amount of chemicals and the size of the cells matters. But when we're dealing with EMF, it doesn't really depend on the size of the cell or the amount of chemicals used. You get it now? Then under the area of the electrodes, internal resistance has an inverse relationship with the area of the electrodes or the plates. So meaning that the greater the area of the electrode, the lesser the internal resistance and vice versa. And under the separation or the distance between the electrodes, internal resistance is directly proportional to the separation distance, meaning that the more distance you have between the electrodes, right, the more internal resistance you will get. You get it now? So this is on the internal resistance of a cell. So let's move on to another concept, which we call the lost volts. So the lost volts is the PD across the internal resistance of a cell. We talked about our terminal potential difference, right? That's our the voltage we know of. We said it's the work done in volts in moving a unit charge from one point in a circuit to another, which is like the voltage when a circuit is delivering current. Don't forget, a closed circuit. Now, when we are talking about the lost volts, we are talking about the PD just across the internal resistance of a cell. And that's why this lost voltage V is equal to what? IR, where this R is our internal resistance and this is your current. We'll get to there. Now, another concept we're going to be discussing on is the external resistance or the electrical resistance of a cell, of a circuit. So this is the opposition to the flow of current in a material. It is represented by R, which is a common symbol we have been dealing with. So this is resistance. Resistance. So good conductors, right? What you know is that good conductors offer low resistance to current, while poor conductors offer high resistance to current. So the poor conductors, which are also referred to as insulators, they offer high resistance to current, so they don't allow current to flow. Then we also have factors affecting the resistance of a conductor. We have the area, we have the length, we have the temperature, we have the nature of the material. Very, very important. Now, how does the area of the conductor actually affect the resistance of that conductor? Now, the resistance, right? Okay, let me erase this. Now, the resistance of a conductor decreases with the area, meaning that when we increase the area of the conductor, right, we get a lower resistance, or we have a lower resistance. So we can represent this mathematically by saying R is indirectly proportional to the area, meaning that as R increases, right, our area decreases. This is what it means. Meaning that for us to have a higher resistance, we have to decrease the area. Or if we increase the area, we get a lower resistance in that conductor. Do you get it now? So yes, let's proceed. So meaning that if you have a thick wire, the thick wire we have a large area. This is what I mean. Let's say something like this now. Okay. Say this is a wire. Good. Yes. Just assume this is a wire. And this is another one. So now, this wire, right, it has a larger area compared to what? This one. You get it? So meaning that for this wire, it will have a lower resistance as compared to this one. This one I will have right here. Because here we're having a smaller area which will surely produce a larger resistance. Good. So moving on, we also have, we mentioned the length, and under the length, the resistance is directly proportional to the length. So the longer the conductor, which in this case is the wire, right, the more the resistance. So R increases as L increases. So if you have this, good, then we have this as the wire. You just have to manage the drawing. And we have this, okay, see. Why am I drawing looking like a snake? Okay, so this wire, right, it will have a larger resistance as compared to what? This one. Yes, so this is under that. Then we also have the nature of the material, which we refer to as the resistivity of the material. So for the resistivity of the material, it is given as this symbol, and we can present the formula as this, R over L. Can you see this now? Or we could choose to make R the subject, and we'll get this. And what you need to know is that if you are looking at this wire, right, remember we said the larger the area, the lower the resistance. The longer the length, yes, then the higher the resistance. Meaning that a short, thick wire has a lesser resistance than a long, thick wire, right, of the same material. You get it now? This is for conductors, for metallic conductors mostly. Yes, for metallic conductor mostly. So if you are dealing with non-metallic conductors, maybe like graphite and others, now you need to know that their resistance actually decreases with temperature. So temperature is also a factor here. We'll talk about that next. Okay, so moving on, we also have temperature as one of the factors that affect the resistance of a conductor. Now, just as we said, the resistance is directly proportional to the length of that conductor, right? Meaning that the longer the length, the more the resistance. It also applies to the temperature of that material. So, okay, I'm just going to erase this quickly. So this was number one. We discussed about the area. So for number two, we talked about the length. And for number three, we'll be talking about temperature. So here, there's a direct relationship between the resistance and the temperature, meaning that the resistance of a metallic wire increases with temperature. Yes, the resistance of a metallic wire increases with temperature. So if you want a higher resistance, right, you just need to increase the temperature. So the higher the temperature, the more the resistance of that wire. Don't forget, resistance is just like the opposition to the flow of the current in that particular conductor. You get it? So now remember, if you listen closely, you will notice that I said the resistance of a metallic wire, a conductor. I said metallic. What if we asked or we asked about maybe the non-metallic conductor? What will happen? Now for non-metallic conductors, right? And a good example is the graphite. The resistance decreases with temperature. Yes, for non-metallic. This is for what? For metallic conductors. That is for this. Now, if we are dealing with non-metallic conductor, their resistance decreases with temperature. So it has an indirect relationship. So meaning that we said the resistance decreases, right, as the temperature what increases. Let me see this. So this is for non-metallic conductors. Good. Metallic conductors. Yes. So a good example of materials that are used for creating standard resistors is the manganese and the constantine. It's spelled this way. This one I'm bringing this up is because these materials, right? They're very important. Wait, let me erase this just a minute. So these are two very good materials that are used for creating or for making our standard resistors that we know of. Why? Is because they are not really affected by temperature. So most times, even if the temperature is increased, when there's a change in temperature, it doesn't really affect them much, which is actually good for accurate results. So moving on, we are going to be discussing another term and we'll proceed. So the purpose of this is just to make sure you understand each and every term under current electricity so that when we start solving questions, it will be very simple. And take note of every formula that is being given. They are all very important. Moving on. Okay, so we also have the conductivity of a material, just as we have discussed about the resistivity, right? Now, this conductivity is the reciprocal of resistivity. Yes, we said resistivity is represented as this formula, is represented by this symbol. Okay, it's presented as this symbol, right? Rho resistivity. So we said resistivity is presented by this symbol. This is resistivity. Now, conductivity is the reciprocal of this resistivity, represented by the symbol. Yes. So, and this brings us to Ohm's law, which is another concept we'll be coming across in this current electricity. So when we solve questions, right, these terms, all these concepts, they are very, very important. So that when we start solving questions, it will be very easy to apply each and every one of them to the questions. So Ohm's law states that the potential difference V across a metallic conductor is directly proportional to the current I flowing through it, provided that temperature and other physical conditions like the length and area of the conductor remains constant. So in other words, under Ohm's law, right, we have V is directly proportional to what? I. And if you want to remove this proportionality symbol there, we need to introduce a constant, right? Here, which will be, the constant will be using is R. Can you see it? So R is serving as our constant of proportionality. So we could make R the subject to give us V over I. Now, one thing to note here is that, as you can see, right, this voltage is directly proportional to what? This current and resistance from what we can see here. The thing you need to note is that if your voltage increase, the current also increase, assuming there's a constant resistance. And if your resistance increases, the current what? decreases, assuming what? Our voltage is constant. Can you see this? So in other words, you can say that a high voltage and a low resistance results in what? High current. And a low voltage and a high resistance results in low current. Then another thing to know about Ohm's law is their graph. And before we can talk about their graph, right? The graph of this Ohm's law, we need to know about two other concepts, which is the ohmic conductor and the non-ohmic conductor. Good. Now under this ohmic conductor, right? These are conductors that obeys Ohm's law, and they have a linear graph between the voltage and the current. When we say linear graph, linear means a straight line, right? Oh my God. Don't mind my line, please. So linear means a straight line. Seems like me and this line is fighting today. So ohmic conductors have a straight line, right? And good examples are metals and the resistor. They're not ohmic conductors. They do not obey Ohm's law. So therefore, they don't have a linear graph. They have a non-linear graph. Good examples of these non-ohmic conductors are your electrolytes, your diodes, and your transistor. I hope you're following. So now, if you are to draw their graph, right, we said that ohmic conductors have a linear graph. Let's look at this graph. There is a very crucial aspect you need to take note of that is asked in exam. Now, for ohmic conductors, right, which obeys Ohm's law, we have a graph like this. This is our V, which is in volts. This is our I, which is in amperes. And we have a straight line. God should help me on this line. Good. Oh my God, are you clapping? So now we have a straight line here, right? Then let's draw another graph. I want you to look at this carefully and tell me what you notice from this graph. Here we have V. Okay. Good. So now there's a line here, just like the first one. So what did you notice from here? 30 seconds, 15 seconds, 10 seconds, 5 seconds. Now, if you look at the two graphs, you will see that there's no more difference. That's just the truth. The only difference is that what? Here we have our voltage and here we have our current. While in this part we have the current and here we have the voltage. Can you see this? So what is the difference? The difference now, they are both both of the graph, they have a linear, they are both linear, right? You have a linear graph for both of them. But the only issue is that their slope is actually different. So the slope of the first one, which is called the VI graph, is equal to the resistance, which is our R. That's the slope of this first graph. Take note of it, it's very important. So this is the slope here for the first one is R. Then the slope for the second, this one, the second graph we have there, which is called the IV graph, is equal to the conductance, is G. So, and the conductance is the inverse of the resistance. So it is measured in ohms per ohms or Siemens. Let me just write this here. So it's the inverse of resistance. I said conductance, right? And this is different from conductivity. Conductivity is the reciprocal of resistivity. So there are two different terms there. All right, so moving on, we're talking about the series and parallel arrangement of cells in a circuit, and then we also talk about the series and parallel arrangement of the resistors in a circuit. So starting off with this, now cells. Remember when we talked about the cells, we said cells, batteries, or any power source, they usually have E.M.F associated with them, right? E.M.F is associated with power sources. While for components, we have the the PD. That's the potential difference. So moving on from here, we are going to consider what happens when cells are connected, what happens to the E.M.F when cells are connected in parallel, and what happens to the same E.M.F when these cells are connected in series. And don't forget, the E.M.F and the internal resistance are closely related. We said that the lower the internal resistance, the greater the E.M.F of a cell. So we are still going to consider what happens to the internal resistance of a cell. That's the small r. So let's start. Now, starting with when these cells are connected in parallel. So let's take the first case. When the cells are connected in parallel, what happens? Now, when they are connected in parallel, the E.M.F of the cells are equal 1 and they are equal to the net E.M.F, which is like the total E.M.F that can be obtained from that cell. So this is what we mean. So if we have the first cell with an E.M.F of E1, another cell with an E.M.F of E2, right? Then the third one, let's say we are making use of 3 cells. When they are connected in parallel, the E.M.F will be the same. So E1 will be equal to E2, and E2 will be equal to E3, and E3 will be equal to E4, and it keeps going like that. So this will be given equal to the net E.M.F. This ET stands for the net E.M.F, and it keeps on going in this order. So this is a net E.M.F, which I said is just like the total obtainable E.M.F right from the cell. So this is what happens when the cells are connected in parallel. Then what happens to the internal resistance? So when they are connected in parallel, the internal resistance, which is R, right, the small r, to get the net internal resistance, which is presented as RT, is given as R over N, where this N stands for the number of cells. So let's draw a diagram so we understand what we mean by these cells connected in parallel to make it easy to understand. So when they're connected in parallel, this is a good example. You can have something like this, because battery, for example, the source of power must have these 2 poles, right? The positive pole and the negative, don't forget. So this is what we mean, this is what we're talking about when we say cell. Please don't see it as one big word, just take it as, bring it to something you can relate with, like the battery, for example. So if we are to draw this now, look at this diagram. You can have something like this. Let's see, we're dealing with 3 cells. So okay, this is a positive pole, this is a negative, then we have this side, then we are having this, also a positive pole. The positive is always longer, then this shorter one is negative. And we have this, then we take this up to get a good diagram. Positive, this is negative. So like this now we can see that 3 cells here are connected in parallel. Why? Because if the current was coming from this place, and you see there will be a branch. The current now will not just go straight again to branch. The part of this current will go here, and just say I1. Another one can go here, you can say I2. Another one can go here, you can say I3. There's a branch, but we'll get to there. We'll get to this place, don't worry about it. So this is what we mean. So this is a good diagram of when it is connected in parallel. So let's move on to when these cells are connected in series. Now, what happens to the E.M.F and the internal resistance? All right, so moving on, we have when these cells are connected in series. What happens to the E.M.F and the internal resistance? So that's case number 2. So when these cells are in series, connected in series, right? Let's analyze. When the cells are connected in series, there are 2 different cases. Unlike the first one where it was very direct, you knew how to get the E.M.F, right? But when the cells are connected in series, there are 2 different cases. But before we talk about these cases, right, what you need to know is that the net internal resistance is the same for both of the cases we are going to be talking about. When we say cases, there are going to be 2 different types of arrangements, and you will see what I mean. So, irrespective of the types of arrangement I'm going to explain now, your net internal resistance, which is RT, will still be given as this. In case you're given 3 cells and you have to find the net internal resistance, right? For the equivalent resistance. Since they are connected in series, you just add them up. This is internal resistance. Don't forget, this we are still going to talk about the external resistance. This is the internal resistance. And when we say internal resistance, we're talking about the resistance of the cell itself, not like external components, external resistors. You get it? So this is like, because that cell must have like a little bit of resistance to the flow of current through it as it's giving out voltage. You get it? So from here now we have this. Alternatively, we can write this as NC, NR, sorry. That is if your cells are the same. If the cells are the same, you can write it this way if the cells are the same. Good. So we are through with this. Now, moving on to the two arrangements we talked about. For the first arrangement, right, this is when the cells with opposite poles are connected. And the second arrangement is when the cells with similar poles are connected. Remember, they are connected in series. But how you connect it in series matters, because when we say series arrangement, this is how it looks like. Let's start with cells with opposite poles. So you saw what I'm talking about. When the cells with opposite poles are connected, how it looks like. So this is how it's going to look like. If you have to draw it, you'll be having something like this. Okay. Then series end to end, right? So the same current is meant to flow through each of these cells. So we're having this positive E1, E2, E3. This is a positive pole, this is a negative pole, positive pole, negative pole. So we're still making use of 3 cells. So this is when this is dealing with opposite poles connected, right? So we have this. This is a very good example. Now, why do we say opposite poles are connected? If you look at it well, you can see that from positive, this is the negative, right? Negative. So negative pole was joined to the what? Positive pole of E2. That's the negative pole of E1 to the positive pole of E2. Now, the negative pole of E2 was connected to the positive pole of E3. Can I see this? So they are opposite poles. When you have something like this, it's very simple to find the net EMF. Very simple. The net EMF, which is given as ET, will be gotten as you just adding each of these EMF together. E1 plus E2 plus E3. Can you see this? And you will get your net EMF. So if these values were different, let's say E1 was 2, E2 was 3, E3 was 4, you just add them up. So if they are the same, let's say E1, E2, E3 are equal to the same value, let's say 2. You can just find your net EMF like this, NE, because E is the same, right? So it's just, instead of you adding up the 3 EMF, which has a volt of 2, an EMF of 2, right? So we just adding them up, you can just say 3 times 2, where N is standing as the number of cells you have. So this is how you get the net EMF when the cells are connected in series with opposite poles connected. So let's talk about when these cells with similar poles are connected. Arrangement number 2. When the cells with similar poles are connected. Cells with similar poles are connected. Now, when the cells with similar poles are connected, right? Most likely they will be wrongly connected because we are going to have like poles somewhere. That's what I mean by similar poles. And that particular cell that is going to be having that's going to be connected with a like pole, right? Will be giving a negative EMF. This is what I mean. Let's give a good example now as we do. Okay, so let's start from here so we get space. So we have 3 cells again. Positive, so this is E1, is going to cell 2. Can you see? There's something I wanted to notice there. Let me draw the last cell. E3 This is positive. This is negative. This is positive. Now this is negative. Good. Then we have this. Now look at this carefully. You see that we have this cell 2, right? Or let's just say cell E2 having its negative pole connected to the negative pole of E1 and positive pole connected to the positive pole of E3. This is not meant to be so. You understand? It's not meant to be so. So because of this now, this cell will be giving a negative EMF. So if you are to get the net EMF, we'll be having it as what? E1 minus E2 plus E3 because this is wrongly connected. Similar poles are connected together. Unlike the first one when we just added it, when the opposite poles were connected, you just add up all of them. You get your net EMF when they're connected in series. You understand this now? So this is what you do. So it doesn't matter. It could be more than even one cell, as you see, that is connected wrongly. Maybe two cells. So this and the other cell that is connected wrongly, you add them up like this. Sometimes you might not even be given a diagram like this. You might just be told 4 cells were connected correctly, have an EMF of this. 2 cells having EMF of this were connected wrongly. Exactly, or with similar poles. So since we already told, let's say the 2 cells, we're having an EMF of you're having EMF of 2 volts. The 2 cells. It's very simple. You know already at 2. 2 times what? Minus 2. Because each of those cells will be having a negative charge to their EMF. Right? So which will give you minus 4 volts. But we'll get there, don't worry. We'll talk about this. So this is under the series arrangement of cells in a circuit. So let's talk about resistors in parallel and resistors in series. That is talking about their own arrangement now. We have finished with cell, we're going to the resistor. Okay, so moving on, we also have the series and parallel arrangement of resistors in a circuit. Remember we said for cells, battery, or any other power sources, they are usually associated with E.M.F, right? Now, when we talk about resistor, here we'll be dealing with voltage. That is the PD. Don't forget, we defined PD, that's the potential difference, right? And then we said it is usually associated with components like the resistors, the light bulb, the LED, the speakers, and all of that. They all have potential difference across them. So moving on to this now. When these resistors are connected in parallel, this is the diagram. This is a good example of resistors that are connected in parallel. Why? Because just as I've said the other time, the current will not just flow direct. If it's series now, we're having something like this. You see that current will just flow to this resistor and keeps going. But here the current will have to branch. Can you see this? It will branch towards here. So this will now be, if this was the total current IT, here it will now branch. We'll now be having I1. Here we'll now be having what? I2. And here we're having another current I3. So here the total current will now be the sum of what? Each of these individual currents going through those resistors. But don't worry, we have not gotten there yet. When we start solving questions, you get what I'm saying. But if you are very smart, just stick this to you. Just take this immediately. Grab it. Because this is a very nice tip I'm just giving you. So we are going to come back to this. So I'm just going to erase this quickly. Let's continue from here. Now, just as I've said, right? We said when these resistors are connected in parallel, we have a diagram like that. What happens? There are a lot of things we need to consider. It's not just you just we just looking at a diagram like this. There's something this diagram actually means, and that's what we're going to consider. Number one is that, okay, let me erase this quickly. The PD across each resistor is the same, and it is equal to the total voltage. Look at these resistors here. We said the 3 of them are connected in parallel, right? If we are to find the potential difference across each resistor, they'll each have their own individual potential difference. But now, the total voltage, can you see this? The total voltage, once you get the total voltage, which we could just use as, let me just say V, let me make use of V. Now, this V is equal to the potential difference across each of them. Why? Because the potential difference across V1 is going to be the same. Let's say potential difference across R1, sorry, is V1. Potential difference across R2 is V2. The potential difference across R3 is V3. they are going to be the same, and this will be equal to the total potential difference because they are connected in parallel. Take note of this, very important. But now, the current is different. The current, that is the current flowing through each of these resistors are different. Remember what I talked about? If this was the total current, this current, when it flows, is going this way, is passing through this, right? The circuit. When it comes here to how to split, part of it will go to R1, let's say I1. Part of it will go to R2, let's say I2. Part of it will go to what? R3, let's say I3. I see this. So here, the current cannot be the same again. It is the voltage that is the same when they are in parallel. So because of this, to get the total current, it will be equal to what? The sum of the individual currents, which is I1 plus I2 plus I3. We get this now. Good. Then this is point number 2. Another thing to note about resistors in parallel is that the effective resistance is given by the reciprocal sum of their individual resistance. This is what I mean. So we have 3 resistors there, right? Providing the resistance. Now, if you look at this, to get the effective resistance, which is like the net resistance, it is given as this 1 over R, or you say RT, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is the effective resistance. If we're having just 2 resistors, there's a shortcut, there's a formula you could use, and it is given like this. To get the effective resistance, R is given as R1 times R2 over R1 plus R2. This is the formula you use if it was just 2 resistors you're dealing with. So take for instance, now we're giving, let's say R1 was 2 ohms and R2 was 3 ohms. So what we do here to get the effective resistance, we just do 2 times 3 over 2 plus 3. And this will give you what? 6 over 5. Can you see this? So if we were to use this same formula, we'll still get something like this. So let's try it out. So we'll be having 1 over RT, or you could just use R. You don't want to, doesn't matter. You know that that's the effective resistance. So this is giving us 1 over 2 plus R2 is 3, 1 over 3. So taking the LCM, we'll be having 6, right? So this is 3 plus 2. And see this, 1 over R. And this will be giving us 5 over 6. So since this is 1 over R, we want R. Taking the reciprocal will be giving us what? 6 over 5 ohms. So any of this formula is still the same. You could also use this formula for 3. It would have been possible to use it for 3 resistor, but the only thing is that you have to take it one at a time. You cannot say R1 times R2 times R3 over R1 plus R2 plus R3. It will not work like that. So another thing to take note of from here is that since we said the current is different, right? Meaning that the current passing through the first resistor, let's say I1, is going to be given as V, which is the same voltage across each of them, because for the voltage is the same over R1. Yes, and then the second current is given as what? V over R2. Third current given as V over R3. This is very important. When you start solving questions, you would need to know, take note of this. So meaning that the current is inversely proportional to the resistance. The higher the resistance, the lower the current that can flow, and vice versa. So let's move on to resistors in series. All right, so now talking about resistors connected in series, what do we need to know? Now, when the resistors are connected in series, it will look like this. So it might be a bit different. It won't always be straight like this. You see it as like this, R1, R2, and all of that. R3. This is still in series because they are joined end to end. There's no branch. If you're having something like this now, we'll say that R2 and R4 are connected in parallel because current is no longer the same. I see this, it's no longer the same. Just going to erase this part. So moving on, when resistors are in series, what you need to know is that the PD across each resistor is different. And the net PD is equal to the sum of their individual PD. So meaning that V here, when they're connected in series, is equal to V1 plus V2 plus V3. I see this, where this V is there is the net PD as a total voltage. You get it now. And it's, this V1 is the voltage of resistor 1, V2 the voltage of resistor 2, V3 the voltage of this third resistor. And now, this is for the first point. For the second one, the current flowing through each resistor is the same and equal to the total current. The current flowing through each resistor, current flowing through the third resistor is equal to each other and it is equal to the total current. Then to find the effective resistance, it's very simple. Unlike the parallel connection, we just have it as R1 plus R2 plus R3. You see this. So for cells in series, V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. So this is to tell you that since the voltage are different, we can use this formula according to Ohm's law. V is equal to IR to get the voltage for each, the voltage across each of these resistors, in case you are being asked. So from here, you will notice that what? V is directly proportional to R, as I is what? Constant. When I is constant, let's say when I is constant here, we have this. So meaning that a higher resistance will have a higher voltage, but lower current will flow. You get it? So what you need to note again is that the resistance of an open circuit, which is, an open circuit is a cell that is not delivering current. It is infinite. It's a very common question. Why is it infinite? When we say the cell is open, no current is delivering, meaning that what? The first thing you need to note is that I is what? 0. So according to this formula, we said V is equal to IR, right? If we substitute, we'll be having what? R is equal to what? V over I. And substituting for I, giving us V over 0. This should be what? Infinity. So this is why we said the resistance of an open circuit is what? Infinite. Infinite. You get it? So we are going to discuss about some extra formulas for E.M.F next, so that you'll be able to attend more questions on this, and maybe one or two other concepts. Then we move on to solving questions. All right, so we are still on current electricity, and I'll be taking more formulas that you should know. That will actually help you to solve more questions under this particular topic. So we'll be going back to E.M.F. We have defined E.M.F, we have learned about some concept of E.M.F and all of that. Now what you should know that this E.M.F is also known as the nominal voltage. So you could say E.M.F so known as the nominal voltage. Good. So now this E.M.F, right? It is equal to the sum of all the terminal potential difference and the lost volts. E.M.F E is equal to the sum of the terminal potential difference, right? The potential difference represents it with a big V, and the lost voltage is a small v. So this is a good formula, one of the most important formula you should know of E.M.F. And then we said our terminal potential difference, which is this V here, is given as IR, right? And our lost voltage, which is a small v, is given as IR. So we could say that where this is our terminal potential difference. Where the smaller V is our loss voltage. Good. So now let's substitute into that formula to get the full formula of our EMF. So substituting, we have E, which is our EMF, will be equal to IR plus IR, that's a small r, just as we see here. So we could choose to simplify further by bringing out I, since I is common to both of them. So we could say E is equal to R plus R. Don't forget, I need to write it here. This I is your current. Okay, so just as we considered the current voltage graph of those conductors that actually follows Ohm's law, right? We are going to consider the current voltage graph of a cell with internal resistance this time around. So we're considering it now. What you need to notice is that here we have something different, which is our internal resistance, R, right? And the graph is actually a descending line graph with a negative slope. So this is what I mean. The current voltage IV graph of a cell with internal resistance. Okay, so we said it is a descending line graph with a negative slope. This is how it looks like. It looks like this. Now explain how we got this. It looks like this. This is a graph. This is I, and this is V. So I want you to follow me shortly. We're going to explain. I'm going to explain something now. You need to know what is the slope. Yes, what is the slope of this particular graph? You know, when we talked about the um the graph for ohmic conductors, right? Which obeys Ohm's law. We said that the voltage current graph is equal to the resistance, while the current voltage graph is equal to the conductance as a reciprocal of resistance. So here now we have an internal resistance here. So it's going to be a bit different. So let me erase this. So since we said that the EMF equal to our terminal voltage plus our loss voltage, right? Making this loss voltage the subject of the formula, we have the V is equal to E minus V, isn't it? Yes, minus the terminal voltage. And then we could rearrange this further by saying V is equal to minus V plus E. Good. Now let's substitute. Since we know that this small v, as the loss voltage, is equal to current times the internal resistance, then we know the big V is equal to IR. So but this time around, we're going to be substituting for just this V. So substituting, we have IR is equal to minus V plus E. So making I the subject, let I stand alone, that's the current. I is going to be giving us minus 1 over R, as we divide both sides by R. So we divide here by R, divided by R, divided by R. So we'll be having this plus E over r. Now we are going to compare this equation, right, that we have here with the equation of a straight line. And the equation of a straight line, is given as this. Given as y is equal to mx plus c. This is the equation of a straight line, where m is the slope and c is our intercept. Now comparing it, what can we see here? If m is our slope, meaning that what? M is equal to minus 1 over r in this other equation. You get it? So meaning our slope is what? 1 over minus 1 over the internal resistance. And then we have our intercept to be what? C is equal to E over R. This is the y-intercept. The intercept on the x-axis, which is this point here, where it touches on the y-axis, sorry, not x-axis. This point where it touches the y-axis. Remember, the I is serving as y-axis. This on the x-axis. Get. So our slope here will be giving us minus 1 over r. The intercept, which is this point, will be what? E over r. Hope you are following. So the intercept will be E over r. So if you look at this, what does E over r stand for? What does minus 1 over r stand for? You will see that the graph of, that is the current voltage graph, right, of a cell with internal resistance. It has a negative slope. That's one. It is a negative slope because there's a minus there. That's because this would come in the Jamb question. It's a very common Jamb question. What is the slope of, what is the current voltage, the slope of a current voltage graph with internal resistance, right? What is the slope? Is it a negative slope, positive slope, and all of that? So you should know that this is a negative slope. And what is the intercept? E over r. Now, E over r is equal to what? I max, your maximum current. Remember, E.M.F is, we said, it's just like the father of the voltage, right? The greatest, that's the your highest possible voltage initially in a cell, before we begin to consider the loss voltage and all of that. So here, the E.M.F, which is just like a voltage over the internal resistance, gives you your maximum current. This is your maximum current. So this is the graph of this cell. So let's move on to the voltage current graph for a cell with internal resistance this time. All right, so the voltage current graph for a cell with internal resistance is also a what? A descending line graph. So what do you mean by this? Let's analyze this. So this is how the graph looks like. This is also a descending line graph. It's going to be looking similar to the first one. The line is descending, not ascending. So we have this. The only difference are here, this is a voltage current graph. So V is on the vertical axis, while I is on the horizontal axis. So what is the slope? How do we get the slope? So going back to this formula, so we said that, okay, E is equal to our terminal voltage plus our loss voltage, right? Yes. Now making this voltage, because we need to know, making this voltage the subject will give us E minus V. And since we know that V is what? V is IR, then go ahead and substitute. V is equal to, okay, let's arrange this, minus V plus E. So going ahead to substitute, we'll be having V as minus IR plus E. So what did you notice here? If you are to compare it to the equation of a straight line, which is y is equal to mx plus c, this being our intercept as said, and this being our slope, you can see that M here is equal to minus R, and our intercept is equal to our E.M.F. Let me see this. So the graph of this voltage against current, it has a negative slope of minus R, and the intercept on the v-axis is E. Yes, so the slope here is minus R, and the intercept on this v-axis, intercept is E, which is our E.M.F. Okay, so moving on, we also have the efficiency of a cell. Now, the efficiency of a cell is the ratio of the electric power output to the power input. So we could say efficiency, which is presented as this, equal to power output divided by the power input times 100, which we could write as power output over power input times 100. Good. Now, what is our power output and what is our power input? Now, this power output is given as I square R. The power input is given as I square R plus your internal resistance times 100. Now, what did you notice? You see, since we have I square in both sides, we could cancel this as I raised to the power of 2, and we'll be left with what? R over R plus R times 100. Good. So if you look at this closely, you would notice that here there's something we could see here. Now we could also write this efficiency as the terminal PD, the terminal potential difference, over the E.M.F. And why is that? Times 100. Why is this? Take for instance, we did not just want to cancel out our I square directly, and we chose to cancel just one of the I. We would have been having something like this, right? IR over I. Let's say we cancel that just one I plus R times 100. Good. So what does this stand for? This is our terminal PD, V, which is equal to this. This is what? E.M.F. I, and E, just E is equal to what? I into R plus R. Don't forget. So this is why efficiency is also equal to your terminal PD times E.M.F. When you're solving questions, this I will surely cancel out. That's why you can just go ahead and cancel out all all the i's from here, the I square, and you'll be left with R over R plus R. You get it? So this is why efficiency is also equal to this, and you could write it as this: P over E times 100. But most likely, when you're solving questions, you're going to use this one, which is E is equal to R over R plus R times 100 to get your answer quickly on efficiency. So this is it on the efficiency of a cell. Take note of this for me, very important. Okay, so let's talk about the wheatstone bridge. This is another concept in current electricity that you need to know. So the wheatstone bridge is an instrument for measuring the resistance of a material. Yes. And another similar term to it is the meter bridge. I'm going to talk about it soon. Now, this is how the circuit of the wheatstone bridge look like, as you can see. Now, if you look at this closely, you see that R1 and R2 are connected in series. Why? Because the current that will be flowing from this E.M.F, that's this power source there, right? Let's say this is it. When this current gets here to divide, out of it to go here, we could name this I3, name this I1, and we could name this I2, we could name this I4. Now, this same current that will flow through this part, will flow through this resistor, and it will still be the same current that will flow through this same resistor. And what happens when both resistors have the same current? It means that those two resistors are connected in series, right? So meaning that I1 will be equal to I2 as the first resistor, that's R1 and R2 are in series. They are in series. So now there's another instrument here. This is a galvanometer. A galvanometer. Now, this galvanometer, don't be confused. You might be wondering what's the current that is going to pass through here. What will happen? Won't it flow? So here, this galvanometer, this, as you can see here, it actually shows no deflection. So meaning that there's no current actually flowing through this galvanometer. You get it? So going back to this, we can also see that I3 is equal to I4 as R3 and R4 are in series. Then if their current are the same for both of them here, meaning that their voltage is different, right? And then, but if you are going to compare R1 and R3, they are in parallel because different currents actually flow through them. And if different currents flow through the two resistors, likewise R2 and R4, meaning that the voltage between R1 and R3 are the same. So meaning that V2, or let's start with V1, is equal to V3 as R1 and R3 are parallel. They are parallel. Likewise, V2 is equal to V4 as R2 and R4 are parallel. Good. So when given question on the wheatstone bridge, you can use this formula to find an unknown resistance. So R1 over R2 is equal to R3 over R4. Yes, so assuming three other resistance were given, you have to find a particular unknown resistance, which will be any of these. So use this formula, make it the subject, and find it. So how do we find the effective or the total resistance? It also has this formula. So the effective resistance is given by this formula. So we can denote it as RT, and for the wheatstone bridge, the effective resistance is given by R1 plus R2 plus R3 R4, or divided by the addition. R1 plus R2 plus R3 plus R4. Okay, so moving on, we have the meter bridge. The meter bridge is the simplest form of the wheatstone bridge. Just like the wheatstone bridge, also use a measuring resistance, a comparing resistance, but it gives a more accurate result compared to the wheatstone bridge. So this is how a circuit for the meter bridge looks like. Yes. So if you are given a question, this is the formula you're going to use. So you could use this formula to find maybe any of the unknown resistance one, or a length, a given length, because we have two lengths. So R1 over L1 is equal to R2 over L2. Or you could also say R1 over R2 is equal to L1 over L2. Here, this L2, which is the second length, is given as 100 minus L1. Yes. So now let's talk about the potentiometer. So the potentiometer is another instrument that is used to determine the actual value of the E.M.F of a cell by comparing it with the E.M.F of a standard cell or a battery. So in other words, this potentiometer actually acts as a voltmeter of infinite resistance. Yes. So it's actually used to get that accurate value, the actual value of the E.M.F of a cell. So this is how the circuit looks like. And to solve question on it, this is the formula we use. E1 over E2 is equal to L1 over L2, where this E1 is equal to the E.M.F of cell A, that's the first cell. Then E2 is equal to the E.M.F of cell B, Then we also have L1, which is the balance point of cell A. And then we have L2, which is the balance point of the second cell, that is cell B. So now, just as I've said, the potentiometer, right, it is used to get the accurate value of the E.M.F. And this is why it is more accurate than the voltmeter. So the potentiometer doesn't really have a pointer like the voltmeter, making it a suitable choice for getting the E.M.F compared to the voltmeter. And this potentiometer, it measures the E.M.F to a high degree than the voltmeter, because the voltmeter might actually have zero error. And then this potentiometer actually measures the E.M.F when the cell is not delivering current. That is in an open circuit. So this is why it actually gives the actual measurement of the E.M.F, since there's no correction for the lost voltage. All right, guys. So moving on, we have another concept to be discussing on, which is the Kirchoff's law. So the laws are actually two in number. We have the Kirchoff first law, or the Kirchoff current law, KCL, and the Kirchoff voltage law, or the second law of Kirchoff. So starting off with KCL, which is also known as the junction law or nodal analysis. Yes, that's another name. So this law states that the algebraic sum of the currents meeting at a junction or a point is zero. The algebraic sum of currents meeting at a junction or a point is zero. Yes, or the total current entering a junction equals to the total current leaving the region. So let's consider this. Let's analyze it carefully. Now, if you look at this symbol, you see that we have about 5 currents here, right? I1, I2, I3, I4, and I5. They are both meeting at this junction O. This is O, junction O. According to Kirchoff current law, right, it can be stated in two ways. So let's take this first one. We said that when you sum up, the first one is just that when you sum up all these currents, it should be equal to zero. And what you should know is that any current flowing towards this junction, the junction where they meet, is positive, while any current flowing away is negative. So I1, I2, and I3 are flowing towards the junction, so they are positive. I4 and I5, look at the arrow flowing, is telling you that it's going this way, right? So this is flowing away. So if you are to present this according to KCL, we have I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. And another way of stating this is that the current entering through a junction, right, equals to the current leaving that junction or the region. That's the second way it is stated. So we can represent this as this: I1 plus I2 plus I3 equal to I4 plus I5. Since I4 and I5 are leaving, so they should be equal to the current entering. So this is on the first law of Kirchoff. You get it, Kirchoff current law. So let's move on to the second law now. All right, so talking about the Kirchoff voltage law, right? Now, this law is also known as the loop analysis law, and it is the second law of Kirchoff. And this law is based on the law of conservation of energy, or the conservation of electrostatic force. And this law states that the algebraic sum of all voltages or potential difference in a closed circuit or a loop is zero. This is what we mean. When you sum up all the potential difference in a closed circuit, it is zero. Now let's see a diagram to explain this, because it can also be stated in another way, which is that the algebraic sum of all the voltage drops in a closed loop is equal to the sum of the E.M.F in that loop. This is what we mean. So here we have a circuit. We have a circuit, and the current is flowing this way from here to here. Good. So now let's analyze Kirchoff voltage law. Now, before you answer any question on this, right, there are some things you need to know again. In KVL, the sign assigned to the voltage, that is, when we say the voltage, we're talking about the E.M.F and your terminal voltage, right? It is dependent on the direction that is shown, where the current is flowing. Yes, depending on that direction. So generally, what you need to know is that, right, when traveling across this loop, if higher potential point, that is your positive pole, is entered, the voltage naturally takes a positive sign. If a lower potential point, that's a negative pole, is entered, the voltage takes a negative sign. Yes. Then your E.M.F, right? This is your E.M.F. It is positive when the direction moves from a negative terminal to a positive terminal. Look at the direction of flow here. It's telling you that your current is flowing this way, from here to here to here to here, and all of that. So since it is flowing in that form, now this current here as is coming, is going to pass through the third resistor, R3, right? And it's going to enter through the positive and what? Come out through the negative. Now, since this E.M.F actually moves from the positive to the negative, right? We'll tag this E.M.F as minus E2. You get it? So this is how you assign various of these signs to your voltages. Yes. So if it flows from positive to negative, it gets what? A negative charge. Then from negative here, like this, negative to positive, E1 will be positive. We're going to write it down. Then another point you need to know is that the voltage drop across these resistors, right, is negative if the direction travels through the resistor in the same direction as the current. And it is positive if the direction travels in the opposite direction with the current. This is what we mean. This current is flowing this way, right? Since it is going this way like this, we said that it is negative if the direction travels through the resistor in the same direction. Because of this voltage flowing in this form, this current flowing like this from this point to this point, and we're told that, okay, this is the direction of flow according to this loop. So this voltage drop across this resistor will be negative because it's aligned with the direction of flow. Same with this resistor. Is this because the current will flow like this and still come here, going in this anti-clockwise direction. You get it? So same with this resistor and also this resistor. So if we are to present this according to Kirchoff voltage law, we'll have this. So according to Kirchoff voltage law, we have E1 because it is moving from the negative to the positive, right? We said it's going to be assigned a positive charge. Then E2 be what? Negative, from positive to negative. Then the voltage drop, they are in the same direction as this flow. So it's going to be negative minus IR. Remember we said voltage drop. We're dealing with voltages. When we're talking about Kirchhoff voltage law, we're dealing with voltage only. So you can't use R, right? Voltage is what? IR. So we're dealing with voltage drops. Good. So we move on. For the second resistor, we also have minus IR2 minus IR3, and then the fourth resistor minus IR4 equal to 0 because the sum of all the voltages, right, will give you 0. Do you get it now? Good. Or we could say, according to the second definition, the sum of all the voltage drops should be equal to what? The sum of the E.M.F. So we could present this as either we do this E1 minus E2 equal to voltage drops plus I plus IR4. Yes. Or you could do it the other way around. You could just choose to write this here, still the same, plus IR4 is equal to E1 minus E2. So this is it. This is how you solve questions under Kirchhoff's law. All right, guys. So moving on, we are going to be talking about the conversion of a galvanometer to an ammeter, and also how we can convert a galvanometer to a voltmeter. So these are two important aspects in current electricity. Very, very important. So let's start with some simple definition. What is an ammeter? What is a galvanometer? What is a voltmeter? An ammeter is an instrument that is used for determining the magnitude of current which is present in an electric circuit, because there is usually this confusion between the ammeter and the galvanometer. Now, the galvanometer is an instrument for detecting the strength and direction of the small current present in a circuit. So while the ammeter is used for determining the magnitude of this current, the galvanometer is used to detect the strength and the direction of that current that is present in that circuit. So now, some major difference between the ammeter and the galvanometer is that the ammeter is calibrated in amperes, while the galvanometer, it's only have divisions. It doesn't have calibration. And the ammeter is more accurate. Listen, the ammeter is more accurate but less sensitive, while the galvanometer is less accurate but more sensitive. Can you see? Good. So, yes, the galvanometer is also called milliammeter. So there are some questions you'll be solving. You'll see that they won't tell you that this is a galvanometer. They'll mention milliammeter. So they're still talking about a galvanometer. Yes. So yes, that's just it. And the reason why it is called this is because it is sensitive enough to measure very small currents. So let's move on. Now, to convert your galvanometer to an ammeter, there's a formula you need to know. In fact, there are some concepts you need to know. It's very simple. One, to make this conversion, you need to connect what we call a low resistance in parallel to the circuit. I see this. So if you look at this now, we have a galvanometer here, right? I want to convert it to an ammeter. Good. So this is a symbol of galvanometer. Sometimes you can see it as something like this. They put a J inside. It doesn't matter. So it's just to know that this is a symbol. Now, this is a circuit. Perfect circuit, right? This is a low resistance. And this low resistance is referred to as a shunt. Resistance of low value, shunt. Good. So when we connect this shunt in parallel to this galvanometer, we can convert this galvanometer to an ammeter. It's a very, very common question that Jamb usually asks. To convert a galvanometer to an ammeter, what do? You connect a low resistance, which is called a shunt, in parallel to this galvanometer. So if you have done that, you can move on. And then this is the formula you use, because most time you may most likely asked to find the shunt resistance, and which is this R. So to find the shunt resistance, we have Ig times R over I minus Ig. R is your what? Shunt resistance. R is your what? Resistance of your galvanometer, most likely the internal resistance of it. And then I is what? Your ammeter current. Good. Ig still remains the same. So with this, you should be able to solve any question that involves conversion of this galvanometer to an ammeter. We're going to be taking more questions shortly. So let's talk about the conversion of a galvanometer to a voltmeter. Okay, so moving on, we're going to be talking about the conversion of a galvanometer to the voltmeter. So the voltmeter is an electrical measuring instrument that is used to measure the potential difference between 2 points in an electric circuit. So how can we convert this galvanometer to a voltmeter? It's very simple. What you need to know is that we are going to be introducing another resistor. So this time around, we are going to be connecting a high resistance called the multiplier in series with the galvanometer. So this galvanometer, you can see connected in series. The same current should flow through both of them. So when you connect this high resistance, known as the multiplier, in series with the galvanometer, you can convert it to the voltmeter. So then when solving questions, you might be asked to find the multiplier resistance value. And this is the formula I use. R is equal to V over Ig minus R, where R is your multiplier resistance, V is your voltage, R is your galvanometer resistance, and Ig is the current of the galvanometer. So we are going to be taking questions now. Let's solve as much question as we can.